Hello and welcome back to another episode of Math with Sohn. Today we're going to be going over some electrostatic things to remember, and I wanted to start with an analogy for voltage, electric field, and charge because they get very confusing very quickly in terms of gravity and in terms of electricity. There's a lot of comparisons that can be made. The voltage would relate to the height of the object that it is if it were thought of as gravity. And the electric field is the acceleration due to gravity, 9.81. And the further away you get from Earth's surface, the less that would exist. So the electric field determines the acceleration and would be what kind of gravity do you have on Earth, would be one electric field, quote unquote, and then one would be different if you had a moon. So a bigger charge would mean a bigger electric field because charge relates to mass. The bigger the charge, the bigger the electric field. The bigger the mass of the planet, the bigger the acceleration due to gravity, okay? So those sometimes get confusing in and of themselves because the electric field creates the voltage and the charge can create the electric field. Now every single particle has its own charge, has its own electric field, and would have its own voltage that would relate to it. And it's the interactions between these two that create the things that get confusing. But it also needs to be understood that sometimes you'll have two charges creating this, and other times it's going to be one electric field caused by either a massive charge or a capacitor. Those are distinct and different scenarios. So on Earth, technically you and Earth are both creating a gravitational field of interaction. But it really doesn't matter because Earth is so big. So that would be in this scenario where you have a massive charge and you would deal with different formulas. If you have two charges, that's when you're going to use KQQ over R squared and things like that. If you don't have two charges, then you have to use different formulas, sometimes with capacitors, sometimes with other ones, but those formulas will not have two Qs. It'll only have one, all right? So that's an important distinguishing difference there. And typically, the Q of the big thing will be uppercase, and the Q of the small things would be called a source charge, and it'd be a lowercase q. All right, so let's look at some things that would relate to that sort of stuff. So here we have two charges, and they're interacting with each other. And we want to talk about here, this is a electric field line. If we wanted to draw the iso lines or the electric potential lines, all right. Oh, by the way, electric potential. Not electric potential energy, but electric potential is just voltage. Voltage. All right. So if we wanted to draw those iso lines for that, then they are going to be perpendicular to the field lines. So they're going to be perpendicular to the field lines. So if we have two of the same charge, you will have this spot in the middle where it's going to not really be able to be perpendicular, and it's going to have to curve this away in order for it to be perpendicular to these field lines. And the first one will be close, and then the next one is going to be a little bit further away typically. If there's a big if there, if we wanted to create field lines in which, voltage lines in which we drop by the same amount. So the closer you get to a negative charge, the more negative that would be. So this we could call negative 30 volts. And then over here we could call it negative 20 volts. And if I wanted to find negative 10, it would be even further away because they get closer and closer as you get closer and closer. Notice how the field gets more dense. If the field is more dense, then the voltage is going to be even stronger because the electric field is even stronger. Okay? Now, these with opposite charges are similar to gravitational fields. Whereas if you have, I think I said this, I don't know if I said opposite. Same charge will be similar to gravitational fields. Opposite charges will not. Opposite charges do not mimic gravitational fields because they will only be, no matter what charge we put here, so this would be, let's say that this is creating an electric field, And if I were to place a source charge in here or a test charge, if I put a positive charge here, little charge, which way is it going to go? Well, it would be repelled from one and then attracted to the other. Because it's repelled from one and attracted to the other, that means that it's not going to mimic gravity because it's repelled. Gravity never repels, it only attracts. Whereas here, when we have two of the negative charges, if I put a positive charge here, it could mimic gravity fields because it would go to and be attracted to both, and it would just end up going to whatever one it's closer to or whatever charge has a stronger electric field at that moment. Okay? Now, it is important to notice that it would only work if you put an opposite test charge and a negative electric field. If you put a negative one, it doesn't mimic gravity. So there are some similarities that can be drawn, but they're definitely different things. Another thing that AP likes to do is they like to say, why do we notice gravitational effects, like the strong gravitational fields and stuff? We feel gravity, but we don't feel the electric forces. And the electric forces are, in fact, stronger than gravitational. So why do we feel the gravitational forces, but we don't feel the electric force? And the answer to that is actually quite simple. That the majority of charges that we have on Earth and the universe end up neutralizing each other. And therefore, the electric fields don't get felt, and we don't have a excess of positive and negative charges. We're net neutral, whereas gravity isn't net neutral. There's masses everywhere, and we end up feeling it. Okay? So, I got another analogy for you. This is going to be, by the way, there's an excellent video by Physics Ninja that goes over this problem, but it is something that is a misconception because most of the time, when you connect two things like this, let's say that this says it has a charge total of 80 nanocoulombs, and a lot of times when you connect the two things, the charges equalize, but that's not always the case. The reason that a lot of times the charges would equalize is because you have the same sphere. But if you have different spheres, some things are going to be different about that. So remember how I said that voltage is equal to height. So let's say that we have two reservoirs here, similar to this. So I'm going to put a big reservoir over here, really wide and flat, and these are going to be connected with a hose, okay? Small reservoir right here. So if these two things can hold water, if they could hold water, let's say originally the water level was all the way to the top, like way up here. And I connected these two with a line at the bottom. Okay, if I connect them with a line at the bottom, what would happen? Well, the water level would become equalized, and then the new water level would be something like here, and then something right here. So the water levels would be the same. And if the height is the same, that means that the voltage will be equal. Now think about that. If the voltage is equal, now we have to think a little bit deeper. If the voltage is equal, that doesn't mean that everything is equal, because the amount of charge normally would be equal, but not always. It would only be equal if these were the exact same container. Because this is a bigger container, it can hold more charge. Quite literally, it can hold more charge. So in this case, this sphere would end up having more charge than the little sphere. And we can prove it with some formulas too. Let's see what we got going on here. Let's see. Voltage is equal to Q over R. And if we take voltage times radius will equal Q, well, because you have a bigger radius, you can store more charge. We have it now visually in terms of like, hey, you can actually fit more electrons or more protons on here. And we have it synonym-wise with the water and whatnot. Okay? So, moving on. We have oh my gosh, I can't remember what it was called. What are these? An electroscope. Oh my gosh, that was a brain fart. So an electroscope, you could bring a charged object to this. like so. So there are two ways that you could get this to move. You could either directly put it in contact, which would be conduction if it is in direct contact, and you could have it induction if it is not in direct contact. Either way, you could get these gold little leaves to move. Okay, in order to move them, you would have to either touch it with conduction or induce that. No matter what, if you put a negative charge here, that would attract, well, let's go with the positive charge. Positive charge makes more sense. So if you put a positive charge here, that means that the electrons that are on, if you put a positive charge, I gotta redo the photos. I thought the photos would be good. If you put a positive charge here, the electrons that were in this leaf are going to shoot up to that spot right there. They would want to do that. And as they move up to that spot right there, especially if it is induced, then you would have a net positive down at the bottom because the negatives would leave and then they would repel. But that would only be known if we knew the charge of the rod. If we don't know the charge of the rod, we would just know that they would still repel, because even if you put a negative thing here, then the electrons would want to leave and you would have a net negative at the bottom. In order to know the actual amount of charge that is on these leaves, or the excess charge on these leaves, then you would have to know a few things. You would have to know the mass of the charge, the mass of the leaf, and you would need to figure out the angle and how far apart they were separated. So you would need to know the mass of the leaf, you would need to know the angle, and you would need to know how far they're separated, but you would not be able to know the exact amount of charge without the mass of the leaves and the angle and the separation amount. You would still not be able to know if they are negative or positive unless we knew what the original rod was. Okay, let's move on to another one. So, there are two types of electric field questions here. You have one where you have an electron shooting through a capacitor, and if it is shooting through at an angle, that would mean that we would have to figure out 2D kinematics in most cases for this. So we have an electric field going up. If the electric field is going up, that means that we have positives on this side and negatives on that side. Okay? And you could think of this literally as a gravity and a ball shooting through gravity. You have to think a little bit more because this is an electron. Which way will the electron want to actually be forced to go? It would want to be forced to go to the positive charges. So it is going to follow this shape right here. It would literally follow a parabola shape because their VI for x would stay the V final for x because there is no force horizontal here. There's only a force downward, okay? Because the electric field is facing up, the force electric here would be facing down because the electron would be wanting to be forced to go to the positive side of this capacitor. It is important to know that this force electric could be found in a variety of ways. It depends on what you're given. If you're given the electric field, then it's really easy. If you're given the electric field, then you would just do force electric over Q. And this Q would be the charge of an electron, which would be 1.6 times 10 to the negative 19. But what if you're not given the Q? If you're not given the electric field of this capacitor, which would be uniform if it is a capacitor, if you're given the voltage of the capacitor, well, then you would just do voltage over radius, okay? And if you're not, and then you would be able to have the E, and you would plug that in here, and you could get your force electric that way. What if you're not even given the voltage? What if you're not given the voltage? Well, there are other ways to do it as well. You could use C is equal to K E epsilon A over D, and you could use that to set it equal to what C is equal to, which is charge of the capacitor over voltage, okay? And then you could find the voltage, you could get the charge, you could do a lot of things. So there's not one clear-cut way to sometimes be able to find the force electric. That's what I'm getting to. Sometimes you have to be able to be like, well, what do I have? I have area. Probably got to find the capacitance, and then I can find the charge, and then I can get the voltage to be able to finally get the electric field. But you need the electric field to get the force. You need the electric field to get the force of the capacitor. All right. We got another one. This one we might do a little bit more with. So here we actually have a voltage difference. Okay, good to know. And we have a radius. And we need to draw the electric field vectors within the capacitor. We have a positive charge over here. And we have not a negative charge, but you can think of it as a negative charge because it's 0. That means that the electric field is going to be going away from this, which is going to want to force this electron to speed up. So in this case, the electron is going to gain kinetic energy, and it will lose potential energy. It could very easily have been the other way around. If we had a proton here, it would have been repelled, and it would lose kinetic energy and gain potential. And the formula for that is, there are two formulas for potential energy. Let's see which one we think we would need to use. U is equal to KQQ over R, and U is also equal to voltage times Q. Okay? Is there another one? I think those are the big two. There's also another one, but it's not going to be this one. 1/2 Q times delta V. The reason why it's not that one is because that would be the charge of the capacitor. So that's why it's not going to be this one in this case. All right. Let's do it. So which one are we going to use? Do we have two charges? We have one charge, not two. We would have to use this guy. Okay? We did have an initial speed, so this is going to have some initial kinetic energy. We do have a voltage, and we have a Q, the charge of the electron. So the energy gained is going to be the voltage difference, which is going to be 200 times the charge of that electron. So that was going to be 1.6 times 10 to the negative 19. That would equal the change in energy of the electron. All right. In other cases, you would have to find the force times distance to get change in energy. So that is another possibility. U is equal to force times distance. If you can get the force electric in a capacitor, it would be assumed to be a uniform electric field, so that would be consistent, and then you just multiply by the separation. All right? So if we were to do this, you would have to start with 1/2 mv squared. Oh my gosh. 1/2 mv squared would equal the original kinetic energy, and then we would add this potential energy, which would be the voltage times the charge, to equal the new kinetic energy, which would be 1/2 mv squared final. Okay? Now, I think that's good. I don't want to go through the math. I hope that you understand that. 1/2 mv squared initial plus the potential that we gained will equal the kinetic energy final, which would be 1/2 mv squared final. Do remember that is the mass of an electron, so plug that in as well. All right. Moving right along. Done that. Did I do that? Yep, I did that. All right. Actual practice problems, then we're going to finish it up. That one's blurry, but sorry. So here we have 1, 2, 3 charges. Each of these charges are producing their very own electric field, each and every single one. Electric fields are a summation. Force is a summation of electric fields in some cases, and in other cases, it's the summation of all the forces. Okay, that would be with 3 or more charges. If you only have 2 charges, you don't need to do a summation. You could just do, if you have 2 charges for force, you can just do KQQ over R squared. But if you have 3, you have to do a summation. Okay, voltage, by the way, is also, voltage is also a summation. You would have to find the voltage of every single one and then add the voltage together. People don't think to do that. They're like, oh, I can just get one and be done. No, find the voltage of every single one. So here it's asking about forces. So the forces of each one, we might not have to do the math, but I think it's smart to do it. Let's see. B, which one are we trying to do? What is the magnitude of net electric force F on each charge due to the other charges? Okay, so I think we're just going to have to do each and every single one real quickly and then find it. So B is going to be attracted to A. It's also going to be attracted to C. So I'm going to do B first because it's in the middle, and that's what I picked. So B would have K Q times 2Q over 1 squared, because the radius is 1. And B would also have K, 2Q, 4Q over, not 3, but 1, 2 squared. That would be B's forces that it would feel. And it would be attracted to both, correct? Because B is attracted to this one and that one, then these two forces would need to be subtracted. Okay, you'd have to subtract those two forces. You would take winner minus loser to get the net force. And that would end up equaling, I'm almost out of room, 2 over 1 minus 8 over 4. Right? 8 over 4. Yeah, 2 over 1 minus 8 over 4. Well, what is that? 2 over 1 is 2. 8 over 4 is 2. That has a net of 0. So the magnitude of B is 0, and that to me tells me that B has got to be at the end or the end. So that means that it's either going to be A or D. Because it said magnitude, it didn't say net. Like, we're not focusing on negatives. All right, so let's see if A is in front. Actually, all we really have to do is see if A is going to be equal to C. Well, A is going to be attracted to B, and it's going to be attracted to B with, we already did that. It would be A and B would have been K, Q, 2Q over 1 squared. But A is also attracted to C, and C would be K, Q, 4Q, and then this one is 3 away. Okay? And it's attracted to B, but it's repelled from C. So that means that, again, these will have to have a minus in between them because they're working in opposite directions. It's attracted to B, it's repelled from C, which means that A wants to go to the left and it wants to go to the right, so they counteract each other to a small extent. So this would be 2 over 1 minus 4 over 9. I don't know what 2 over 1 minus 4 over 9 is, but I'm going to save that for the final one, which is C. Man, this is getting messy. I'm sorry. C has, with B, we already did that, 2Q, 4Q, and 2 squared, which we already confirmed was 2. And then with A, we already confirmed it was 4 over 9. It was Q and 4Q and then 3 away. So minus, probably minus Q, 4Q, over 3 squared still ends up equaling 4 over 9. The question is, are we going to have 2 minus 4 over 9 or 2 plus 4 over 9? Well, C is attracted to B, so it wants to go to the left, but it is repelled from A, so it also wants to go to the right, which again means we have to subtract to do all of this to confirm that they are in fact equal. So A it is. Whew! All right, I'm not going to do too much more. The video is getting long. Here, we have a two-dimensional thing, and the only thing I want to talk about with this is the fact that sometimes you have to think in x's and y's, and you cannot you can't mix the streams. You have to do x's for x and y's for y's. It says, what is the magnitude of the net exerted force on object x by w, y, and z? Object x is right here, and everything has a charge of q, 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 q. So that means that it is going to be repelled from W and repelled from Y. If it's repelled from W and from Y and they're the same distance away, that means that those two repellings are going to be equal to each other and X is not going to go left or right. So we really only have to figure out what is it going to do from Z. Well, Z also is going to be repelling it, pushing it upward, and if that is the only force we have, it will go up. And that will be a force of the force that of W on X is F. Well, Z is twice the distance away, so that means KQQ over 2 squared will be 1/4 the force. That's how I would think of it. So I would think of this as like a radius away, and I would think of this as 2 radiuses away. But you didn't have to. You could have done the math slightly different. If this is 1 radius away and that's 2 radiuses away, it is going to be 1/4 the force. Okay. Last one. 3 identical conducting spheres are supported by an insulated thread. Initially, blah, blah, blah. Initially, one has a positive, and the other 2 charges are uncharged. By the way, it's going to probably say that you touched them. But even if they were not touched, if this is still neutral, the neutral will be attracted to a positive charge. What will happen here is with the positives being here, they're all the way around the edges if it is a conducting sphere. And here, if this is a conducting sphere, the positives will repel and end up being on this side, and the negatives would attract, and then eventually those two would be attracted to each other, and they could touch. And if that happened, then this would be a net positive. And if this is a net positive, then the same thing would happen to sphere 3, and then eventually those could touch, and then this would be a net positive. So here, I think that they're brought into contact and then separated, but they would still end up with a net positive on all three if that were the case. Okay? Now, it is important to know that these are conducting spheres. If they were insulating spheres, then it would be probably a little less likely, but insulating would have a cluster of positives on one side. Or it could become polarized, where the individual atoms in the molecules could be like positive, negative, and then positive, negative, where the individual atoms end up doing that. But it still can make it kind of a net positive on one side and a net negative on the other side, and the atoms will literally stretch a little bit, creating some like elastic energy within the atoms, which is kind of cool. That they kind of act like a rubber band, because once they get out of that electric field, they go back to where they would. All right, that's going to do it for this one. I'm sorry if I rambled. I hope you got something out of it. See y'all later. Bye.